Hello, Royals. Let's take a look at lesson 6.4 on velocities. I specifically want to talk about the geometry of a couple of questions. First one I want to take a look at is the second part of the car question. In the car question, we are told that car A is traveling at 100 kilometers per hour east. That can be labeled as the velocity of the car A relative to the ground. And in my lesson and in your textbook, you'll see different ways of reporting this. This seems to be a pretty popular way of writing it. I think the current equation editor that I'm using has a hard time with subscripts on both sides. So you might see me doing more of just this notation. I'll accept all of those notations there. In the second part of the question, instead of car B just going west, we say the car turns to travel west 30 degrees north. I go west and then turn 30 degrees to the north. I could draw this vector anywhere. I'm just deciding to place it at the same origin as this first vector. There's 30 degrees to the north. That is the velocity of car B relative to the ground. It has a magnitude of 120 kilometers per hour. If you're having trouble visualizing the diagrams, I'm going to strongly suggest you start with an equation, because the equation is relatively easy to write. If we're looking for, and the question asks us for the velocity of car B relative to car A, so how does it look like car B is traveling from someone's reference point in car A? Then you just need to do a bit of almost like a chain rule here, almost like tip to tail addition for vectors. If I want to go from B to A, then I'm going to have one vector that has an initial reference of B, and I'm going to add that to another vector that has a final reference of A. I'll link through the ground here. Now, this might not make a ton of sense if you just sort of try to see it right here, that you're going to be adding the velocity of the car B relative to the ground, and then you're going to be adding the velocity of the ground relative to car A, because we don't think about the velocity of the ground relative to car A very much. But our idea of just adding an opposite of a vector will work just fine here. Let's do the velocity of car B relative to the ground minus the opposite of the velocity of car G, or sorry, of the ground relative to car A. And that's going to give us the velocity of car B relative to the ground minus the velocity of car A relative to the ground. Now, to perform a subtraction, I'm just going to add the opposite. Here's A relative to the ground. Oops. Yeah, no, that's right. Here's A relative to the ground. Here's the opposite of A relative to the ground. So I'm going to be adding those vectors like that. And there's my resultant. Now, this should make sense as well. If you're in car A, it's going to look like car B is going sort of, I guess, back and to the left, or west and to the north of you. But this is by how much and at what angle. Just be careful about getting lost in your diagrams if they get a little bit too crowded here. This 30 degrees turns out not to be too useful over there. I think this angle of 150 degrees, the supplement of 30 degrees, is more useful because it lies inside this triangle. There's a parallel line theorem, opposite interior angles. PLTZ. If you, like me, find that your diagrams are getting a little bit crowded, then just draw a new one without all of the rows directions in the way and all of the angles that you don't really need. Like, I don't really need that 30 degrees right now. I need that 150 degrees. I need this magnitude of 120. I need this magnitude of 100. I feel like even the units might get in the way a little bit. And then this is my resultant here. I'm looking for the velocity of B relative to A. Okay. And that's where I get my cosine law from in the lesson. See if you can follow that solution. For example 2, I just want to point out in the diagram originally provided on here, there was the distance of 800 meters. I think that the value might have been left over from a previous question, or it's just an example to show you that you don't always need all of the numbers. The number 800 meters doesn't come up in this question at all. maybe we should be able to figure out how long it would take us to cross or how far downstream we're going to end up. But that's not what this question is asking. The reason why I scratched it out is this is a velocity diagram, and 800 is not the magnitude of a velocity. Maybe if I was going to do this problem and have to figure out how far down the boat is going to drift, I should have one velocity diagram and one displacement diagram. Okay, example 3. With airspeeds. It's strange how usually students do okay with boats in water questions. That's probably because they can think of water as being I don't know, like I don't want to say solid. I guess solid enough medium. Maybe they have experience swimming across a river and they see that if they're trying to swim north but the river is flowing east, they're going to go northeast. That if they want to end up going north, you're going to have to swim northwest so that when the water pushes you, you end up just going north. Well, the same is true with air, and I just don't think that most of us have much experience with that. How many times have you been trying to land a plane approaching north, and there's I don't know, runway going north, but there's a wind going east? If you just point straight for that runway, the wind is going to blow you off to the side. Don't you hate it when that happens when you're trying to land an airplane? Yeah, it's just not a situation we find ourselves in too often. Let's stick to our formulas and stick to our diagram here. So we have a plane scheduled like that wants to end up 600 kilometers at a bearing of 60 degrees. Let's draw the bearing of 60 degrees. That's also known as north, 60 degrees east. 600 kilometers, 60 degrees. I might need that 30 degrees there as well. Let's just label everything. Okay, that is the intended displacement of, oh, sorry. I'm actually, once again, I think I'm going to want this to be a velocity diagram. So I'm going to scratch that out. I don't actually know what this velocity is going to be or its magnitude is going to be. I think I need to figure that out in this problem. But this will be the velocity of the plane relative to the ground. That's where I want the plane to end up. If there was, because there's a wind blowing in this direction, the plane is going to have to point in a different heading. Let's say that the wind was blowing east. Maybe the plane would have to aim a little bit more to the north so that the plane would fly in this direction and the wind pushes it east. But an observer from the ground would see a plane sort of pointing in this direction, going in that direction. Okay. It wouldn't be that extreme, but what else are we given? We are told that there is a wind blowing from 280 degrees. 280 degrees is west 10 degrees north. But be careful when you draw that vector, that is the wind blowing from there. This happens a lot. You're usually not told in what direction the wind is blowing. You're told where it's blowing from. Okay, let's label that as a 10 degrees. I'm going to move this vector so that it's down here. I mean, I could place this vector anywhere I want because the position of a vector doesn't affect its definition. 10 degrees. And this is a velocity vector. I know its magnitude is 100 kilometers per hour. That is the velocity of the, what do we want to call it? Air or wind? What did I do in the lesson? Can't really see. I guess it doesn't matter. Let's do wind relative to the ground. Okay. Now, what I'm missing here is, and what I'm asked for is the bearing that the pilot should steer at. And then to figure out how long the trip is going to last, I probably need the velocity of the plane relative to the wind as well. I'm told that the plane has an airspeed of 300 kilometers per hour. That's not this ground speed. A plane's ground speed is how fast it's going over the ground. A plane's airspeed is how fast it's going in the air. The air, just like the water in the previous example, is moving, which will either increase or decrease or change the ground speed. So we have, let's say, the velocity of the plane relative to the ground. We could make an addition here and say that's going to be the velocity of the plane relative to the wind plus the velocity of the wind relative to the ground. So what I'm missing here is the velocity of the plane relative to the wind. This is my resultant. I want to add tip to tail from this velocity of the wind relative to the ground. I think I'm just going to switch the order around and say this is going to be the direction in which the plane will have to steer. One of these angles, I'll probably end up reporting maybe this angle right here or this angle right here. Hard to tell. Okay, there's the velocity of the plane relative to the wind. If you don't like looking at it this way, you could maybe make a parallelogram out of this. What sometimes students do fine with is imagining in a river question, imagine you could dam the river and you let the person swim directly across and then they stop and they tread water. Then you turn the water on and they drift down. Well, imagine this with a plane or maybe I don't know, a blimp or a helicopter or something like that. You let the helicopter fly, then you tell the helicopter, okay, now you need to stop, and then the wind is going to push it the rest of the way down. Or start here, start with the wind. You say go, and the wind blows it here. Now you say, okay, wind, now turn off. This is how you're going to have to steer. And what this is going to look like, again, to the observer, is your plane pointing its nose in this direction, and the wind is just pushing you the entire time, and you end up right here. Okay. Go nuts with your parallel line theorem in here. You've got this angle being 10 degrees, so that's 10 degrees, so this is 80 degrees. You've got a 30 degrees in there, so you can use a parallel line theorem. I think you end up using the sine law in this case. Tidy up the diagram and see if you can follow the mathematics from the lesson. I don't want you stressing out too much about physics. We just completed a day or a lesson on forces and velocities, but we do have plenty of other stuff to do in this lesson. And I don't like this when in a regular class when we would have a regular test at the end of this unit. I don't want it to be a physics test. Still, you should be able to answer the homework questions. There is a question very much like this in the homework. Take it carefully, take it slowly, make sure that you have the wind pointing in the right direction, and think about writing out these formulas first to make sure that you have the directions right in your diagram. Okay.